Hello and welcome. Okay, today we're gonna be considering some kind of stuff on ordinary differential equations. I'll put the title up there. Some ordinary differential equations analysis. It's not the mathematical analysis in a formal way. It's just a little bit of a discussion, and it's gonna be improvised. So we're gonna make up a question, and hopefully we'll be able to solve it and just consider a few bits and pieces. The level of this lecture, you're gonna need further maths, so it's actually further maths based. But the second part, I hope to go to a little bit of undergraduate stuff, so it might not be accessible to everybody. So let's start first of all. Where we're gonna start? We're gonna make up a differential equation ourselves. So let's start by starting with some kind of implicit expression, such as perhaps I don't know, x cubed plus xy squared minus 4 I don't know, let's put it the other way around, x squared y is equal to let's make this into a minus and make this into a plus, is equal to some number, and not to find what number, of course, it needs to be. I'll pick, for example, to satisfy the condition 1, 1. So our curve is going to the point 1, 1. So this is actually very easy. That's why I actually changed the plus with the minus this way. So it can give me a positive constant here. So that's 1 minus 1 plus 4 is equal to 4. So we have nice numbers. So this is our curve. I'm going to put it up there just in case we need it later. Okay, because of course we're gonna set up a differential equation and we're gonna solve it and want to know if we've done it correctly. So this is basically what we're starting with. So x, that's how a question is being made basically. So I'm giving you an insight into making questions as a former examiner. This is what you will be doing if you're making a question of differential equation, perhaps. Okay, so we're going to differentiate it in order to come up with the differential equation. So implicit differentiation now. I'm not going to be showing a lot of working. So we're differentiating with respect to x. What happens there? We're going to get 3x squared. We got the product. So product rule, differentiate the first bit is a 1 times the second bit unchanged, so that's a y squared. Now leave the x bit alone, we still have a minus, and then you differentiate the y, so it's going to be 2xy dy by dx. I hope I don't make mistakes today because I'm very, very tired. I just come back from the gym and I'm brain dead at the moment. Plus, we got another product there, so we're going to get there an 8x when we're doing the first bit, times the y, and then we're differentiating the second item on this product, which is the y, which of course is going to give us plus 4x squared dy by dx. And of course the 4 will differentiate to 0. So all we need to do is just to form the differential equation by collecting the dy by dx terms. So that's going to give me 4x squared minus 2xy lots of dy by dx, keeping track of the terms, this one and this one, and I'm going to shove this to the other side, and this will mean I will be having equal to y squared from there, and I'm going to have, it doesn't really matter in what order I put them, minus 3x squared minus 8xy, and eventually we will have a differential equation which will say, of course, dy by dx is equal to y squared minus 3x squared minus 8xy, the whole thing over 4x squared minus 2xy, subject to the condition, of course, that the curve goes to the point 1, 1 basically. So it's y is equal to 1 at x is equal to 1. Okay, so we made up the question. We know what the answer is because we made it, of course. We have a differential equation, but if we didn't know the answer, now we'll be looking at this, and that looks very, very scary. It's definitely laughing at us, okay? And our task here is to actually make sure that this goes to a corner and is actually scared of us rather than laughing at us. So how we're gonna do it is the question. Okay, this is now further maths. So I'm going to, I'll try to see how it's best to use the board. I'm going to be doing a little rubbing. So I'm going to leave the differential equation here, and I'm going to be doing workings up there. in further maths, I have to stress, a differential equation like this, which you're expected to solve, they will give you a substitution, okay? But for us now, we're not at A level, we are just mathematicians or applied mathematicians perhaps, and we have to think how we're going to approach this. And this particular equation is very, very special. It's a first order and is known as a homogeneous equation. What that means formally is you can write it in the form homogeneous for a first order. The word homogeneous means many different things depending on which context you're using it. So sorry, my spelling is disgusting. I'm not quite sure how to spell this. It should be like that perhaps. Homogeneous. It means that it can be written in the form dy by dx is some function of y over x or x over y if you want. So if you look at these terms here, if I divide top and bottom of this particular fraction on the right by x squared or y squared, I'll either get y over x or x over y all the way through. But the brain picks it up a lot easier. If you look at all 5 terms on this fraction, they're all quadratic. Squared, 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 x times y, squared, squared. So this is a homogeneous equation. How do you solve homogeneous equations? You need a standard substitution, which I'm going to write there. The substitution that works for this type of equation is y is equal to x v of x. So x times v, where v is a function of x. And with differential equations, your plan is to, apart from substituting that obviously here, is you need obviously to replace your dy by dx. So of course we need to differentiate it here, dy by dx, and let's see what happens. This is a product, so it's going to be the differential of x is 1, I'm not going to write it, times v of x, plus leave the x alone and differentiate your v of x with respect to x. So that's d, oh gosh, d by dx of v of x. Perhaps I should just drop the arguments there. I'm going to write it again. Of course, v is a function of x, so dy by dx is simply v plus x dv by dx, where of course it is understood that your v is a function of x. So let's now transform the O.D.E. I'm going to rub off this condition, it's up there. Okay, so what happens now as we're putting things in? Okay, we're going to have v plus x dv by dx. All good. I hope we're not getting any funny noises from the microphone because it's been very, very problematic. It's really getting on my nerves recently. Is equal to, and now I'm transforming the right hand side. So y is xv. Let's write it, let's lose the x from here as well. It's very annoying. So this will become x squared v squared minus 3x squared. Okay, and then we got, of course, minus 8x minus 8x, and then I'm going to put a y that will create another x to make it squared, but I'm going to get a v there. So this is from the term minus 8xy. The 4x squared is 4x squared. Nice to meet you. And this one is minus 2x, and the y is another xv. So it's going to look something like that. Okay. So what happens next? If you now see what happens, and this is why this works basically, is all of these 5 terms that have an x squared, which I can cancel through, and note x cannot be 0 because, of course, if you look at the original O.D.E. here, x and x, if they're both 0, we're having a problem. Okay, so this will now reduce. I'm going to do 2 things at once. I'm going to put x dv by dx, and take that v to the other side, but at the same time cancel this particular fraction. So this will become a v squared minus a 3 minus an 8v over the x squared goes 4 minus 2v, and of course I got the minus v from the other side. So this is what has happened so far with my differential equation. Let's make some space, and what do I do next? This will be separable by the looks of things. So I need to put everything into a single fraction. So v squared minus 3 minus 8v minus 4v plus 2v squared, the whole thing over 4 minus 2v, and x dv by dx. Tidy further, I'm going to get 3v squared minus 12v, those two, minus 3. I got a factor of 3. I'm just wondering what I'm going to do with that. I'm going to think about it afterwards. Over 4 minus 2v. What am I going to do next in this particular one? I'm going to separate my variables, so that will flip when it goes to the other side. So it's going to be 4 minus 2v, the whole thing, over 3v squared minus 12v minus 3 dv, and the x will go as 1 over x on this side dx. Okay, so that's definitely separable. I'm going to take a breather, start rubbing the board, and just think about what I'm going to do next. Don't know if you can actually see what we got in there, and just perhaps think what's this integration all about. It doesn't look pretty. I can see that doesn't factorize, so for partial fractions or anything like that. I can see there's a factor of 2 there, the factor of 3 there. What I'm going to do, of course, is what I preach to my students. First of all, we got the fraction. Does the bottom differentiate perhaps to the top? Because it'd be nice if I had 2 logs on both sides. That's definitely a log. This gives me a 6v minus 12 when I differentiate it. So it's gonna be a v twice. Bingo. This is bottom differentiation to top. It just needs a bit of work to do it, and I hope we don't make a mistake. So how are we gonna make it? Okay, first of all, I'm gonna leave it the bottom as it is in there. I don't think I'm gonna touch this. I need to create a 6v minus 12 on the top. So to make a 6v, I need to times top and bottom by, not top and bottom, and times both sides of the equations rather, of the equation by negative 3. That will switch me into this. So this will go times negative 3, 6v, times negative 3, negative 12, and the denominator, of course, is exactly the same. I'm not timesing top and bottom of the fraction, I'm timesing both sides of the equation, yeah? 3v squared minus 12v minus 3 duv is equal to negative 3 over x dx. I think we're in business. This looks quite nice now. So this integrates instantly. So that's the log of 3v squared minus 12v minus 3 is equal to negative 3 log of mod of x. And of course we got a constant, and a constant, if we have loads of logs, me personally I will not put a plus c. I'm gonna say plus the log of a, where of course the log of a is just another constant. And I'm going to perhaps save myself a line there. I don't want to copy all of this just to take care of this negative 3. So what I'm going to do, I'm going to take this negative 3 inside the log and write the argument of the log as 1 over x cubed. I hope you allow me. And of course these two logs now I can put them together. It's addition with multiplication of arguments, so we can actually write it as something over x cubed. And of course now we can get rid of the logs. So this now becomes 3v squared minus 12v minus 3 is equal to a over x cubed. We need to in order to evaluate this constant, we need to go back into x, and our substitution now, v stands for, I'm going to put it here, v is y over x. So we need to put that back on the left hand side. So we're going to have 3 y squared over x squared minus 12y over x minus 3 is something over x cubed. We can tidy this very easily by multiplying the equation through by x cubed, and this will give us 3 2xy squared, because we've got x squared there, of course, minus 12 yx squared minus 3x cubed is equal to a constant a. Okay, probably it's a good idea to divide by 3. So it's going to be x y squared minus 4 yx squared minus x cubed. The constant divided by 3, you can call it still a if you want, doesn't matter, another constant. Let's call it b, so we do things a little bit more properly, because I'm very sloppy with my stuff sometimes. Okay, and perhaps looking at the answer, it's there. You can see it's we just got the negative of it, so this b will turn out to be negative 4 if we put our condition in. So if we put now the condition 1 1, this is going to give us a 1 minus 4 minus 1 is equal to b. So as we're expecting, the b now is going to be a negative 4. Okay, so let me just rub it off, because I don't want to be writing it again. Negative 4. And of course, if we multiply the equation by negative 1 both sides, we're going to get x cubed positive minus x y squared from this bit here plus 4yx squared is equal to 4, which of course is what we had up there, and we managed to tame this particular differential equation, which after all we made it, but we have to discuss basically to actually identify that this is a homogeneous equation which works with this particular substitution. We've done what we had to do. I think the workings in the middle of that, they were not that bad, but they were not straightforward either, but we did manage to come up with the answer, so we have done it. Okay, so this is now the standard way of doing this, but there is, and I'm going now to perhaps undergraduate level. Do I have the original differential equation? The answer is I don't, and I'm gonna have to differentiate it again, because I'm very, very bad. As I said, this session is improvised, and I should have really written the O.D.E down, so now I don't have it, because I'm going to do it in a different way. And if you allow me, actually I didn't want to do this here. I'm going to write dy by dx. Those who have done partial differentiation, maybe they understand what I'm doing in here. I'm just going to come up with this very, very quickly. With respect to x is 3x squared with respect to x minus y squared with respect to x plus 8xy. With respect to y, goodbye. With respect to y, 2yx negative, 2xy negative, 2xy negative. With respect to y, plus 4x squared, and therefore I got the minus at the front, so this will be plus and this will be minus. And so let's just double check this. With respect to x, I'm getting 3x squared. With respect to x, I'm getting minus y squared. With respect to x, 8xy, and the bottom gone. With respect to y, 2xy negative, which gets positive from that minus at the front, and with respect to y, 4x squared minus. Okay, let's hope. I think I've done it very quick. I didn't want to do the implicit differentiation as I've done it before. I hope I haven't made any mistake and now have a completely different differential equation, because this will be quite laughable, really. You can laugh at me, I guess. So this was the differential equation, and we've done it, of course. It's a homogeneous. We could, obviously, it's a standard A-level technique, but sometimes it's worth looking at something else when you're having equations which look like this. Okay, I'm going to rewrite it in a very special form. So what I'm going to do is I'm going to multiply across. So I'm going to say 2xy minus 4x squared times dy is equal to, in a bracket, 3x squared minus y squared plus 8xy dx. And now I'm gonna write it with this on the left and this onto the right hand side, but swap it. So you'll see in a minute what I'm doing. I'm writing 3x squared minus y squared plus 8xy dx, and this now I'm going to move it to the other side, but I'm writing it on the left. So what that means, instead of putting a minus here, I'm going to write this as positive and this as negative. So 4x squared minus 2xy dy. Okay, and of course that is equal to 0. Okay, so why have I done that is the question. For those who know partial differentiation, this looks like the standard differential of a function. Let me just write it. You can call it phi, you can call it capital F. D capital F, let's say, is partial f with respect to x, dx. So this is your dx. So this is your partial capital F with respect to x, this item here, plus partial of f with respect to y, dy. So of course that matches that. And if this particular differential equation is exact, in other words, I can undo the implicit differentiation essentially, which I know I can because of course I made the question, so that's it should work here unless I made a mistake there, and of course this will not work. Is I need to do a little check. The check for exactness is, of course, this is the partial of capital F with respect to x. I'm going to differentiate this with respect to y and this with respect to x, and if the answer is exactly the same, then this particular thing is actually invertible, if you want. I can actually undo the differentiation, the implicit differentiation. So I'm going to differentiate this with respect to x, so that is 0. With respect to x, sorry, I'm differentiating, no, I beg your pardon, it's with respect to y I'm doing, I beg your pardon. With respect to y, yes, it's 0. With respect to y, I'm going to get minus 2y. And with respect to y, I'm getting plus 8x. And this one, I need to do with respect to x now. So this is going to give me 8x from this term here. And this with respect to x is going to give me minus 2y. Bingo. And exactly the same. I'm expecting them to be, of course, the same in our case because we did do this implicit differentiation. So the question is obviously doctored. It's not that it shouldn't happen, but I was worried, as I said, just in case I've done the mistake up there. So what does that mean now? What it means is I can actually find my f by simple integration, if you want. So this is going to be now, if you want, I'm going to use a different color pen. Let's use green pen because I need a little bit more bold space. This is my partial capital F with respect to x, and this is my partial f with respect to y. And I know it works because I've already checked for exactness and I got the desired result. So I'm going to do this bit first. What does that mean? You'll see in a second. As I was explaining earlier on, this is undergraduate level. I don't know, some universities don't even bother with things like that, applications to differential equations, but you should be able to follow what I'm doing. Partial of f with respect to x is, of course, this thing here. 3x squared minus y squared plus 8xy. So I'm going to integrate. So my capital F with respect to x should give me an x cubed, this bit here. Integrating this with respect to x is going to give me minus y squared x. And integrating this with respect to x, so y is a constant essentially, is going to be increase the power of x by 1, so it's going to go x squared. The y is a constant, and 8 divided by 2 is a 4, plus 4xy, and of course we have the constant of integration. The constant of integration is not necessarily a constant because we're differentiating a function of two variables, and we differentiate with respect to x. This in general will be some function of y, because of course if we differentiate with respect to x, this would have disappeared. Okay, we're going to do the same thing now with the other one. So this should be a lot easier. 4x squared minus 2xy, and now this is integration with respect to y. So my capital F, I'm integrating with respect to y, so this is just a constant, so it's going to give me a 4x squared y, and this is with respect to y, so this x is a constant, so I'm increasing the power of y by 1, and I divide by the new power, so the 2 will become 1, and the x of course is a constant, plus another function, but this time, because we're differentiating with respect to y, in general will be a function of x. So of course this, that is an f of, I should really have written it here, f of x comma y. Okay, so it's a function of x and y, this capital F's. So I just need to compare now sides and just see what I've got. Let's use a red pen. So 4x squared y, 4x squared y. So my f of xy, which of course is equal to some kind of constant, is going to be equal to 4x squared y, because it appears on both. I also have an xy squared on both. So I should have a minus xy squared. I don't have the x cubed on both sides, so what does that mean? Does it mean it's not there? Not really. There's also a b of x there, so that b of x, okay, it could have constants, like when I say constants, constants like a 7, but it definitely has that x cubed. I'll pick this bit by comparing that and that, okay? And of course there's no function of y as such on the other side, so this is at most a constant, and therefore I can just shove it into equal to c if you want this constant there. So now what I've got up there, and if you look at the differential, not the differential equation, the equation, the implicit equation I started with, I hope I haven't made any mistakes. X cubed minus x squared y plus 4x squared y is equal to c. You will spare me, and I'm sure if we put the 1 1 we're gonna get a 4 there. So this is of course all done. I don't know if that made sense. That's the second part of the lecture. This is for undergrads quite clearly. You need to have working knowledge of partial differentiation, these expressions which are now rubbed off, and this is a very useful technique sometimes in solving certain differential equations. And for those who are just wondering, now that I've done all of this, what I was doing up there, I don't know if anybody who is an undergrad and he's seen partial differentiation and implicit expressions and things like that was actually following. For implicit equations of this form, your dy by dx is in fact, if you call this is equal to, let's call it minus 4 is equal to 0, and you call this bit here your phi of xy, your dy by dx is always equal to d phi by dx over d phi by dy. And sometimes, you know, when I'm teaching at A level and one of my students has done his implicit differentiation and I want to check their answer very quickly, of course I'm not going to do the long way that they have done. I just check it by just doing that, and that's merely that formula that I've just written up there, just rearranged really, and that's all there is to it. Okay, so I hope you find this useful. I hope you kind of like understand what we've done in here today, or part of it at least, and I'll see you very soon, and I'm definitely laughing now. Okay, bye for now.